combinatorial way. Now, let me talk about one of the most beautiful graphs in graph theory, as mathematicians often say, especially those who work with this graph. It's Petersen graph. Petersen graph first appeared in a paper by Kemp, and it looked in this way. But it has a name by Julius Petersen. Here is the paper, here is how it looked in Petersen's paper, and here is the most traditional drawing of Petersen graph. So whenever, if you Google, if you open an article about Petersen graph or a book, you always see this drawing. And actually it appears in a number of, on the cover of some mathematical magazines, because it's really popular graph. So as you can see, this is a symmetrical drawing of Petersen graph. This is another drawing of the same graph, and it also has some symmetry, right? You can see there is rotational symmetry of, we can rotate this sort of circle on this angle, yeah, and the graph will stay the same.
No. Are you sure?
Yes.
Will be reflection.
Reflection?
Reflection. The rotation.
Rotation as well. Yeah, reflection, yes, and rotation, well.
How about that horizontal line there? Oh, okay. Yeah. Okay. Yeah. Yeah.
It's sometimes it's tricky. So nevertheless, in Petersen's paper, the graph appears in this way, and you can see there is no visible symmetry in this drawing. So this is an example when you can have visible symmetries and invisible symmetries. Mathematicians also say hidden symmetries. What is so remarkable about Petersen graph? So they say this is a page from the book The Petersen Graph by Holton and Sheehan, 1993, and they make a historical reference that it first appeared in Petersen's paper, but also they say it was appropriate that the graph was used as a counterexample in his paper, because, as we shall see, it contributes to be a yardstick with which to measure conjectures. It also has many interesting properties. These two facts give it a unique place in the theory of graphs. What he means here under a yardstick with which to measure conjectures, it just happened that Petersen graph has appeared as a counterexample to many wrong conjectures in graph theory. A counterexample, so say somebody suggests a hypothesis, a conjecture, a beautiful theorem or formula, but when they try Petersen graph and consider this conjecture, would it work or not, it turned out no, it doesn't work. And somehow mathematicians keep trying their conjectures on this graph, exactly on this graph, and it works very well. So this is one of the reasons why it became so popular. So as I said, this one is the most favorite drawing of the Petersen graph. How many symmetries can you see in this graph? 5. Which ones?
Just the rotation.
Rotations. Okay, you can rotate. This is the angle. This is the angle to rotate the graph. Yeah. If you rotate it 5 times, it will be the same. Yeah. Okay. Given identity. Any more?
Perhaps 10 if you change the inside with the outside.
This is an interesting idea.
There's also reflection on the sides.
There is reflection in respect to vertical line, yeah.
Yeah.
But you can see that there are other lines, there are other 4 lines additional to vertical. This one, for example, yeah, or this one, and this one. Therefore, we can have 5 reflections. 5 rotations, 5 reflections give us 10. And in fact, this is the maximum you can see, you can visualize in one drawing of a Peterson graph. It's a matter of fact, yes, it's a mathematical fact that this drawing is maximally symmetric drawing, and 10 symmetries is maximal you can depict in one drawing of the Peterson graph. However, how many symmetries there are in fact in this graph? 120. Yes. Striking, isn't it? So, this is what I mean when mathematicians are talking about hidden beauty or hidden symmetries. Yeah. And as I said, there are different drawings, and some show some symmetries and some not. For example, this drawing doesn't show us this kind of permutation. 1 goes to 4, 4 goes to 7. 1, 7, 4. I'll show you in a minute. Yeah, this drawing, for example, it has 3 rotations, right? So you can see 3 rotations, but you cannot see those 10 symmetries which you can see in the previous drawing. That's what I mean. Yeah. So it's impossible to see all of symmetries in one drawing, and what is also impossible to visualize is the combinations of these symmetries. Because if you think combinatorially, if you take one reflection, and if you take a rotation, you can combine them, you can make one after another in combinatorial sense. You see what I mean? Yeah? But in this drawing, you cannot do that. You cannot depict it in one drawing. In a series of drawings, maybe, but not in one static drawing, just to make it clear. Okay. Let me come back to the issue of mathematical beauty. So, in my first premises, I said that symmetry is a candidate for a contributor to mathematical beauty, so far, and we distinguish between visible and invisible symmetries, right? And our question is how these two things correlate with each other, and how they help mathematicians to make aesthetical judgments about these objects. For example, Peterson graph. So there is often frustration that we don't have this. We cannot see. We cannot see 120 drawings, 20 symmetries we cannot see them, yeah. There is this kind of emotion about that. But there is also an admiration that there is so much of hidden beauty in this mathematical object. And we may be able to discover this beauty. So this emotion could be contributors to judgments about the beauty of Peterson graph. So I showed you this drawing already, and here is another picture. So symmetries may be helpful to be visualized, to work with them. Yeah. nevertheless. Although we can calculate all of them by using some formulas, we can calculate 120, but it's very often useful to see them, to visualize them, to understand the structure. So this is a new one, you probably didn't see it before. It has how many symmetries? It has, what do you think? Just reflection, just vertical reflection. Yeah, and sometimes it's quite hard to figure out how to draw these symmetries, how to visualize these symmetries. So mathematicians try to find some ways. For example, this kind of video, you can see what's happening. The first traditional Peterson graph visualization and the second one, which was in the middle. So you can see how one symmetry can kind of go into another. This is this example. Why I use these visualizations is just to make a point that mathematicians are really working on this issue, on this problem, visualizing as many symmetries as possible, because presumably it's useful for mathematical reasoning. And there are some works in computer science, so computer scientists raise this issue. Well, it's useful for mathematicians to have symmetries visualized in order to work with them. And why don't we, computer scientists, solve this problem? How to visualize, how to draw graphs in the most symmetrical way. And symmetrical is only one property, a desirable property. Of course, there may be other desirable properties mathematicians would like to have in visualizations. Let's see what they are. So, this is a quotation from a computer science paper. Symmetry is one of the most important aesthetic criteria that clearly reveals the structure and properties of a graph. Graphs in textbooks on graph theory are normally drawn symmetrically. In some cases, a symmetric drawing may be preferred over a planar drawing. Let me explain a couple of things here. When he's saying aesthetic criteria, here aesthetics is taken in terms of applicational aesthetics. It's applied aesthetics. It's a technical term in computer science. It's not about beauty in philosophical sense. Yeah? It's just it's a branch in computer science which is working on visualizing things in mathematics. Okay. And another thing which is important here, he stresses that symmetry helps to see the structure of the graph. And here is an example of two graphs. This is actually an example of one graph, but two drawings of the same graph. In the first graph, you have symmetry. Yeah? This is a symmetric graph, and this is the same, but not so symmetrical. Yes, it has a reflection symmetry, but this one has more symmetries. And the author is saying that this graph appears in publications and articles and textbooks much more often than the second one. So this is more useful drawing of the same graph than this one. Not only computer scientists, but also psychologists, cognitive psychologists, are thinking about this problem. So they took a group of people of different mathematical background, even without mathematical background, and asked them to draw a graph, given that such and such vertices are connected with such and such vertices in this way. They draw graphs, and then they were asked, they draw like several pictures, and they were asked, could you please choose one which is the best, the most clear, the most understandable. And here are the properties, the list of properties they came up with. What were they saying? fewer edge intersections. What I mean here, here's just an example of one graph. Here is an edge intersection in the drawing. Here, this is not a vertex. Yeah, this is not a part of a graph. It's just a property of the drawing. It's not a property of the graph, but a property of the drawing. Okay. And people are saying that the less such intersections you have in the graph, the better. Then, straight edges preferable over curved edges. Straight and these are curved. Then 3, vertical and horizontal edges are preferable. No lines are preferable to lines under other angles. So, well, I think it's clear. Vertical and horizontal alignment to grid, so something like when you have a net and the graph is kind of fit to this net, it's very useful. Subgraphs or sections with some patterns, symmetric subsections is very important, yeah, which correspond to the previous slide, yeah. Large angles. So here, for example, the angles is very narrow, but here some angles are large. So people prefer larger angles, and also important nodes on the top. But well, here in this picture we don't have important nodes. So there is a very close correlation between what computer science say and cognitive psychologists also say about graph drawing. Now, let me talk about beautiful and the ugly drawings of the Peterson graph. So here are 2 pictures. This is a traditional one, as I said, and somehow mathematicians are keeping saying, this is our favorite, this is the most beautiful drawing of the Peterson graph. Yeah, remember, at the beginning I said the Peterson graph is one of the beautiful graphs in graph theory, but now I'm talking about drawings of the Peterson graph. We are talking about visualization, yeah? And we are talking about perceptual beauty solely, yeah? Just to keep you in the frame. So, what can you learn from this? And then they say, and this is, thank you so much for your remark, when you were saying that if you take the star from the pentagon, stretch it outside, you will actually have this drawing. Yeah. Can you see that? You just pull out the star from the pentagon, take these edges out here. Yeah. That's what you have in this drawing. Now the star is outside the pentagon. A pentagon here, the pentagon is outside the star. So definitely we didn't change much. Yeah. We didn't change the structure of the graph as a mathematical object. We only changed the drawing. And interestingly enough, we preserved the same symmetries, right? Both drawings have the same number of symmetries, and they are the same symmetries, absolutely. So, there is a question now for philosophers. Look, these 2 drawings have the same number of symmetries. One is called ugly. They call this ugly. How they got it? If you give a task for a computer, as I said, there is a branch of computer science to draw the graphs in a particular way. So you give the parameters to the computer of the Peterson graph. There are some particular parameters, right? The computer will draw you more or less these 2 different drawings. So the mathematicians say this is a beautiful one and this is an ugly one. They have the same symmetry, and the question is what's wrong with this one? For a lay person, for a non-mathematician, well, it's hard to say. Somebody say, oh, this one is also pretty, and maybe somebody will say, oh, this is actually better than, more beautiful than this one. What's wrong with this? This is quite nice. So the question is, what mathematicians mean when they say that one is ugly and one is beautiful? Well, I think that the first has more good properties. Good properties, I mean the properties which I listed in the previous graph, in the previous slide from cognitive science, psychology experiment, research. Then the other one. What I mean here, the angles, the inner angles are much broader in this first drawing, right? Here there are narrow angles, and here we have larger angles. So here, for example, this angle is very large compared to these angles. Also, here we have less edge crossings, less edge intersections. Yeah, we have 1, 2, 3, 4, 5, but here we have also 5, but there are more edges intersecting here, right? So I would say in this drawing we have kind of more noise in the sense that it's much more difficult to get the information about the structure of the graph from the second drawing than from the first drawing. Yeah, would you agree? I think so. So I think the traditional wins because it has less sort of additional irrelevant elements, perceptual elements, which keeps you away from appreciating the mathematical structure. So my hypothesis is that mathematicians call these more beautiful mainly because they perceive not only the perceptual beauty of this, the harmony of lines, the visible symmetry, but also they see something more about this graph. They see some mathematical beauty of this graph. And this drawing, the way how the drawing is organized, helps them to appreciate these properties. Whereas here, they are too busy with looking for the mathematical abstract structure. They are busy with grasping. They are struggling with extracting this mathematical structure from a little bit messy drawing. Yeah? And this keeps them away from appreciating the beauty. They keeps them away from arriving to the aesthetical judgment that this is a beautiful graph. So this is what I think, and so far let me recap what we have. Different drawings reveal different mathematical properties, symmetries. Yeah, symmetrical drawings are more beautiful because, as mathematicians say, that the traditional most symmetrical drawing is the most beautiful. So we can draw the conclusion that symmetrical drawings are more beautiful. Second, particular visual properties help one to grasp mathematical properties, structure. Particular properties, I mean visible symmetries, broader angles, fewer edge intersections. But some representations mathematicians call beautiful because they like them for practical reasons, convenient to work with. What I mean here is this is just a remark. This is a new thing. This is a new thing. What I mean here, we have to distinguish the aesthetical judgments from practical judgments. And I want to stop here and let you think a little bit about it in the break, during the break, and I will explain it in detail later. Thank you. Let's have a break, 5-10 minutes.